Most years, the inner solar system only hosts a small handful of comets, but in late 2025, the skies will witness something extraordinary. 7 major comets, diving inward almost at the same time, including the interstellar giant 3I divided by Atlas, which continues to swell in brightness. Astronomers are now tracking this unprecedented gathering, charting their paths as they rush past Earth and the Sun in a compressed 6-month span. Some scientists even suggest this surge could influence solar activity, and at least one of these visitors may flare bright enough to be seen with the naked eye. But why are so many appearing together now? And what kind of wonder or risk could this cosmic traffic jam bring? 7 sizable comets crowding into the inner solar system during a single season is almost unheard of. In a typical year, sky watchers are lucky if 1 or 2 bright comets pass close enough for detailed study. 3 in the same year is already remarkable. But 7, all plunging in within a matter of months, is the kind of occurrence that stands out across an entire century of astronomical records. Since the era of systematic sky surveys with projects like Pan-STARRS, Linear, and the Atlas program, no observing season has ever matched this level of activity. The last time comet numbers came close, astronomers were still photographing the sky on glass plates, and discoveries often came by accident or word of mouth. What makes 2025 so striking is not only the total count but the timing. This isn't a slow trickle stretched over years, it's a concentrated rush, with each comet weaving its way through the inner solar system in rapid sequence. Some arrive from the distant Oort cloud, others are returning periodic visitors, and 3I divided by Atlas doesn't even belong to our solar system at all. That interstellar outsider alone would be headline-worthy in any other year, but paired with 6 additional major comets, the odds become astronomically slim. On average, since the year 2000, only 1 comet per year has grown bright enough to be seen without optical aid, with perhaps 2 or 3 more requiring binoculars or small telescopes. Many years pass without a single naked-eye comet. Even in so-called comet showers, when several arrivals cluster together, totals rarely exceed 3 or 4. According to public data from the Minor Planet Center, no digital era season has ever featured more than 4 major comets with perihelion inside 2 astronomical units, and that doesn't even account for the unusual orbital alignments this group is showing. It's worth noting that modern surveys have dramatically increased discovery rates, but the vast majority are faint, short-lived, or too distant to excite the public. Truly bright and accessible comets remain rare gems, which is why the 2025 wave stands apart. So improbable that astronomers are calling it a statistical anomaly, a spectacle that might happen only once in several generations. That's why this isn't just a catalog of icy bodies, it's a phenomenon in itself, a genuine swarm that disrupts the usual rhythm of our solar system. With so many visitors arriving in near unison, astronomers are treating the 2025 surge as a single, multi-act performance. The focus is no longer just on individual comets, but on their collective choreography, how their paths, alignments, and solar encounters might overlap or interact. It's this rare convergence that fuels both scientific excitement and public anticipation. Before we unpack the details of terms like perihelion, superior conjunction, and ecliptic alignment, it's worth pausing to recognize just how extraordinary it is to see 7 major comets sharing the same stage in one season. The first act belongs to C divided by 2022, N2 Pan-STARRS, which defines the opening of the 2025 comet season. It will reach perihelion on July 31st at a distance of 3.82 AU from the Sunday. Its orbit keeps it far beyond Mars, in a region where sunlight is weak and only the most powerful telescopes can follow its faint progress. Pan-STARRS sets the outer boundary of the swarm, a quiet overture before the drama builds. Next comes C, divided by 2025 R2, Swan, discovered on September 11th and racing to perihelion just a day later, on September 12th, at 0.5 AU. The highlight will be its close pass on October 21st, when it sweeps by Earth at only 0.25 AU, about 37 million kilometers. This makes Swan one of the best candidates for observation, especially in the pre-dawn skies of the northern hemisphere. Its swift motion and geometry provide a rare opportunity to study a comet's interaction with both the Sun and Earth in near real time. On September 27, 414 divided by stereo makes its solar loop, reaching perihelion at 0.52 AU. Its orbit dips beneath the ecliptic plane, often lost in the Sun's glare, making it difficult for ground-based telescopes to track. But for spacecraft observations, this trajectory is ideal, offering a unique vantage point for solar studies that Earth-based observers can't match. Then comes C divided by 2025 K1 Atlas, arriving at perihelion on October 8 at just 0.33 AU, closer to the Sun than Mercury itself. This perilous pass guarantees rapid transformations, making Atlas a prime target for monitoring outbursts, jets, and tail evolution. Its proximity to the Sun puts it right at the heart of the swarm's activity. The spotlight then shifts to the interstellar traveler, 3I divided by Atlas. On October 21, it reaches superior conjunction, disappearing behind the Sun from Earth's perspective. Just days later, on October 29, it swings through perihelion at 1.36 AU within Mars's orbit. With an inclination of about 5 degrees, this outsider tracks close to the ecliptic, sharing the celestial stage with planets and other comets alike. For several days, both Swan and 3I divided by Atlas hold critical positions for solar interaction studies, though neither will be easy to spot with the naked eye. On November 8, C divided by 2025, a 6 Lemon reaches its peak, grazing perihelion at 0.53 AU. Unlike some of its counterparts, Lemon remains visible after sunset, offering one of the most accessible viewing opportunities of the entire group. Predictions suggest it could brighten to magnitude 4 or even 3.5, potentially visible to the unaided eye for Northern Hemisphere observers in early November. Finally, 240 divided by NEAT closes the sequence, reaching perihelion on December 19 at 2.12 AU. As a periodic comet, it's fainter and more distant, but its arrival underscores the crowded, almost chaotic state of the inner solar system by year's end. 7 comets, each with its own timing, path, and story woven together into a once-in-a-generation spectacle. Each comet's orbit, perihelion timing, and alignment with the ecliptic together create a densely packed calendar, laying out the framework for the solar interactions to come. Comets aren't just icy travelers trailing pretty tails, they are living records of the unseen forces shaping our solar system. As a comet draws close to the Sun, its nucleus warms and vents streams of gas and dust, forming 2 distinct tails. One is a broad, pale dust tail, the other, a slender, electric blue ion tail. The ion tail is especially revealing. It traces the invisible hand of the Sun's magnetic field. Built from charged particles, it is pushed outward by the solar wind, a constant outflow of plasma and magnetism streaming away from the Sun at hundreds of kilometers per second. Yet this tail is fragile. It can be torn away in moments during what scientists call a tail disconnection event. The underlying physics comes down to magnetic reconnection. As a comet travels through the solar wind, it occasionally crosses abrupt shifts in the interplanetary magnetic field caused by a coronal mass ejection or a brush with the heliospheric current sheet. These are anything but smooth transitions. The magnetic field can swing by 90 degrees or more in mere minutes. When it does, the comet's plasma environment can't keep pace. The old ion tail detaches, drifting silently into space, while a new tail immediately begins to regrow, perfectly realigned with the altered flow of the solar wind. One of the clearest examples came in April 2007, when NASA's Stereo spacecraft captured a CME colliding with Comet Encke. The ion tail was sliced off in a single strike. A visible gap opened near the nucleus as the severed tail floated away. It was a near-perfect confirmation of magnetohydrodynamic models, frame for frame. Such events become more common during solar maximum. With multiple comets plunging near the ecliptic in late 2025, the chances of witnessing a live tail disconnection are higher than usual. The dust tail, on the other hand, is far less sensitive to these magnetic tempests. Governed mostly by sunlight and gravity, it takes only the most powerful CMEs to strip away or distort part of a dust tail, typically by blowing off a chunk of the coma or deflecting the dust outflow. For skywatchers, the sudden breaks and regrowth of the ion tail are the real signatures to look for visible proof of the sun's restless energy written across millions of kilometers of space. Solar physicists are preparing with equal parts excitement and caution, because beyond the spectacle lies a deeper question. Could this comet swarm actually stir the sun itself? Some research groups, notably NASA's CCMC modeling team, suggest that the sudden influx of cometary plasma and dust, especially from those aligned with the ecliptic, might increase the likelihood of solar outbursts or even amplify their intensity. Simulations indicate that when an active, dust-rich comet cuts across the heliospheric current sheet or drifts into the path of a coronal mass ejection, the magnetic field geometry can rearrange abruptly, sometimes setting off a classic tail disconnection. In these models, the sun's magnetic field lines bend and wrap around the comet. If a CME strikes from just the right direction, the ion tail can snap away in minutes, leaving the comet to immediately grow a new one. The CCMC's magnetohydrodynamic runs suggest that with several comets plunging through the inner system during solar maximum, the likelihood of multiple striking disconnection events rises significantly. Their models even hint that the surplus plasma released might seed fresh instabilities in the solar wind itself. But not all scientists are convinced. Teams working with ESA's Solar Orbiter and NASA's Parker Solar Probe point to their own in-situ data, which paints a more subdued picture. They've logged numerous small bends, ripples, and twists in comet tails that never escalated into full disconnections even in the middle of strong CME encounters. Their field readings suggest that microscale turbulence, localized reconnection, and the background variability of the solar wind often dominate the outcome, sometimes more than the large CME impacts. From this perspective, the sun's broader magnetic cycles and large-scale polarity flips are the real drivers of major space weather, with comets acting more like tracers than triggers. These researchers caution against overstating the risks to satellites or terrestrial power grids, noting that even the dramatic 2007 Encke tail loss event had little measurable operational effect. Still, with CME activity expected to spike to 2 to 5 eruptions per week during the late 2025 solar maximum, both sides of the debate agree on one thing: this is an extraordinary opportunity to put their theories to the test in real time. Space weather centers are tightening their monitoring networks, and amateur astronomers worldwide are preparing for coordinated campaigns. If a major disconnection unfolds while a comet is in view, the event could be documented from backyard telescopes all the way up to interplanetary spacecraft. For now, the debate has only sharpened the community's attention. Every new CME, every odd twist or fracture in a comet's tail could tilt the balance in this scientific standoff. And then there's the wildcard 3I divided by Atlas. When astronomers first charted its orbit, the numbers didn't match any known family of solar system comets. Its trajectory is hyperbolic, with an eccentricity well above 1. In plain terms, this comet is not bound to the Sunday. It is passing through the solar system on a one-time journey, never to return. That fact alone makes it historic. Only 2 other confirmed interstellar visitors have ever been observed: Oumuamua in 2017 and 2I divided by Borisov in 2019. But Atlas is different in more ways than one. Early measurements from the Hubble Space Telescope and the James Webb Observatory suggest its nucleus lies somewhere between 320 meters and 5.6 kilometers across, potentially far larger than either of its predecessors. The coma, that luminous shroud of gas and dust streaming off its surface, has already ballooned to nearly 700,000 kilometers across, almost the size of Jupiter, and it continues to expand week by week. Unlike typical comets that spend billions of years frozen in the far reaches of the Oort cloud before venturing sunward, 3I divided by Atlas hails from far beyond, likely expelled from another star system. It carries material born in a completely different stellar environment. Its chemistry confirms the alien origin. Spectroscopic data show a coma rich in carbon dioxide and volatile gases, with only faint traces of cyanide and a surprising scarcity of water vapor. These chemical fingerprints are unlike what we normally find in local comets. Its motion tells the same story, entering at a steep hyperbolic angle, skimming the ecliptic by just 5 degrees, and moving with a velocity that leaves no doubt this traveler is interstellar. The scientific potential is immense. Each dataset offers a chance to compare the raw building blocks of other planetary systems with those of our own. But the stakes go beyond chemistry. As Atlas swings past the Sun, it will shed a trail of interstellar dust and debris that Earth could intersect in 2026, giving planetary defense teams a rare opportunity to examine foreign material up close. The saga of 3I divided by Atlas is still unfolding, but already it is redrawing the boundaries of what we thought our solar system could contain. From late October through early November 2025, the skies will deliver a rare treat for comet watchers. And you won't need advanced gear, just clear conditions, some patience, and the right timing. The show begins before dawn on October 21st, when C divided by 2025 R2 Swan makes its closest pass to Earth at just 0.25 AU. Even through simple binoculars, Swan's tail could span an incredible 2.5 degrees across the sky, about 5 times the apparent width of the full moon. Its head is expected to glow around magnitude 6 to 7, faint but reachable for anyone willing to rise early and scan the southeastern horizon. From mid to high northern latitudes, Swan climbs nearly 40 degrees above the horizon at civil twilight, making it an ideal pre-dawn target. At the same time, 3I divided by Atlas slips behind the Sun at superior conjunction. While ground-based telescopes lose sight of it, the spotlight shifts to spaceborne solar observatories. Instruments like SOHO's LASCO C3 coronagraph will keep tabs on Atlas and occasionally Swan, as well as faint specks gliding against the backdrop of the Sun's outer corona. These real-time feeds are publicly available, inviting anyone to join the global effort to catch sudden flares, outbursts, or even a dramatic tail disconnection triggered by solar activity. By early November, C divided by 2025, a 6 lemon takes center stage in the evening sky. Forecasts suggest it could brighten to magnitude 4, or even 3.5 under dark skies bright enough to spot with the naked eye, especially for northern observers just after sunset.